Hello guys, this is Ehsan. In today's video we're going to talk about this circuit, and we're going to find the minimum and maximum value for this resistance RB in order to all of the transistors work in saturation region with this data available. But before we get started, if you're new here, please give me a thumbs up, hit that subscribe button, and also the notification bell. So let's jump into it. This is our problem and these are all the options. But before we jump into solving this problem, try it by yourself. Try to pause the video and try it yourself. This is the circuit, and I'm gonna start this problem with this information. This is information number 1 and this is information number 2. From 1 and 2 we can get that VGS minus V threshold equals to 0.2 and V threshold equals to 0.4. So we can get the result for VGS, which is equal to 0.6 volt. This is the VGS for all of these transistors, because this information for all of these are just the same. If there were any difference, they should mention it, for example by subscript, for example VGS1, VGS2 or something like that, but all of VGS equals to this one. So just for the sake of simplicity in this problem and to make it clear to solve this problem, I'm gonna draw VGS into these circuits. I'm gonna actually put the information into the circuit. This is 0.6 for VGS1, this is 0.6 for VGS2, and this is 0.6 for VM3. And just to make life easier in my follow-up calculations, I can clarify this node here, the voltage of this node here. If you're using KVL, you can see that in this loop we have 0.6 plus 0.6. So here the voltage is 1.2 for this node here. Now, in order for a transistor to be in a saturation region, it had to be two conditions. First, VGS must be greater than V threshold, which is true for all of these transistors based on this calculation here. Okay, and another condition is that if this condition satisfied, which is satisfied in this problem, the gate drain voltage of transistor and NMOS transistor must be less than or equal to threshold voltage. Okay, so we have to check these conditions for all of these transistors, and after that we can get the conclusion for the suitable range for RB. So starting for M1, V gate drain of 1 equals to, what is the voltage gate? Gate is equals to 0.6 minus the drain voltage of this transistor, which is here, something like here. Okay, so how we can calculate this? Just following this path, starting from here, 1.2 minus, what is the current through this RAB? This is IB. Why this is IB? Because the gate voltage of NMOS, which is this one here, equals to 0. Gate doesn't have any current in it. So what is the voltage drop across RAB? It's RAB times IAB. And just move on, and here we have 0.6. Because I'm using this root, the voltage drop in the value of 0.6, so minus 0.6. And now we can get to the drain 1. So this gate drain must be less than or equal to threshold voltage. Now I'm going to simplify this by crossing out some numbers. So here we have 0.6 minus 1.2 minus times minus plus RAB IAB minus times minus 0.6 plus 0.6 less than equals to V threshold 0.4. So these two and this one cross out, and we have left with RAB IAB less than or equals to 0.4. This is the first condition to consider. Now move on to the second transistor, V gate drain 2. How about this one? This is the gate voltage for M2. And if you're taking this route, you can get the result quickly. 1.2 minus RAB IB, and now we're here, the gate of transistor M2. And this is the drain of M2. With respect to ground, you can set that this is the voltage of M2, 0.6. So minus 0.6 less than or equals to threshold, which is 0.4. So you can transfer RAB IAB to the right hand side to make it positive. So RAB IAB is going to be greater than and equals to 1.2 minus 0.6, 0.6. And by transferring this one to the left hand side, 0.6 minus 0.4, 0.2. So this is the second condition to consider. How about the third one, about M3? What is the gate drain voltage of 3? This is gate. Gate equals to 1.0. Be careful, for every node you had to know the voltage of that node with respect to the ground. So here I had to write 1.2 for gate of M3. And how about drain? Here this is the drain. Starting from here to there, minus 1.2 minus RAB IAB less than or equals to 0.4. So it's obvious that 1.2 minus 1.2 are crossed out, plus RAB IAB less than or equals to 0.4. So these are crossed out, and we have RAB IAB less than or equals to 0.4. So this is the third condition to consider. And if you just look at these options, you can set that these two are just the same, so take one of them, and this is another option. So we have a range for RAB IAB. Out of these three conditions, we can set that RAB IAB is greater or equal to 0.2 and less than or equals to 0.4. And with IAB equals to 50 microampere, I can divide this size to the IAB to simplify this, and at the same time divided by this number, divided by IAB, which is 50 microampere, less than or equals to RAB 0.4 divided by 50 microampere. So what is the result for this one? We can set that if we want RAB in kilo ohm, which is options in the question, we can use milliamp for this one. So this is 0.05 milliamp. 0.2 divided by this number, you can multiply this by 100, and you can set that this is 20, this is 5. So this is 4 kilo ohm for the left hand side, 4 kilo ohm, and for the right hand side you can set that this is with some simplification 40 divided by 5. So this one is 8 kilo ohm. This is the final result for this problem, and from these options you can set that option 4 is the right answer. I hope you like this video. If that's the case, please give me a thumbs up, and if you have any questions, let me know in the comment section. See you in the next video. Thanks for watching.